James Webb images of nearby galaxies. There's a handful of them here. We have a growing sample. And what I'm trying to highlight here is the richness in the gas structure that we're observing now. That's all the stuff that's appearing in the reddish orangey colors. Now, by the end of today, hopefully I will have described to you exactly how that gas structure emerges. How does it form? And as it turns out that the physical processes that are responsible for the amplification of the spirals that we see in the gas disks are exactly the same as leads to the formation of spiral arms in stellar disks. So I think that's probably where we should begin, which is looking at stellar disks. This is probably the context where you're most familiar with looking at spirals. What do we know about spirals? One of the main characteristics, of course, is that they're observed across multiple wave bands. We see them when we look in red bands, tracing the old stars. That tells us that they are in the stellar mass distribution and gravitational potential. And we also see them when we look at bluer bands, right? And that tells us that the bluer bands are where the young stars are, and that tells us that the spiral has an impact on the gas and young stellar distributions. Now, that's what I'm showing you here. We've got sets of galaxies, and as you progress, as you get bluer and bluer and lower mass, as it turns out, the properties of the spirals tend to change. So the pitch angle of the spirals, how tightly they're wrapped, the number of spiral arms, right? And this is nothing other than Hubble's tuning fork, right? So you all are familiar with this. We start on the left-hand side with the massive early type galaxies. They're old, red, and dead, right? And they're smooth and structureless. When we move to the fork, we enter the disk-dominated regime, rotationally supported. We see smatterings of evidence of star formation, and this is where we start to see the spirals. Now, Hubble already had in his classification this tendency for spiral properties to change as you change the global galaxy properties, right? And this is something that we've now shifted from just this qualitative description for the relationship between spirals and their host galaxies, and we've made it more quantitative thanks to surveys like Sloan, right, and projects like Galaxy Zoo, which showed us just what the disk properties were for a galaxy of a given pitch angle. That's what's shown here on the bottom right. So we have this well-known correlation between optical color, right, and stellar mass. And we've added an additional piece of information here, which is the pitch angle of the spiral. And just like we saw with Hubble's tuning fork, right, we see that as galaxies become redder and redder and more massive, the pitch angle gets smaller and smaller. Spirals get tighter and tighter wiped. And there's this correlation here. But one of the things we still don't know after all this effort, right, is whether we're actually adding something unique and new when we add this third parameter, the pitch angle, or is it just repeating what we already knew, which was the color and the mass? Relatedly, we don't know if the pitch angle and the spiral properties are a consequence of the disk properties, or if somehow they are affecting, for example, the color, right? Somehow are they leading to star formation that wants to change the global color of the galaxy? Now, one of the other things that we often don't know, but I wish we knew better, is whether the stellar spirals that we observe are quote-unquote Lin-Shu long-lived density waves, probably you're familiar with this concept, or whether they're material patterns. They're just local agglomerations of stars and gas that are going to shear out some point later. This is actually really difficult to distinguish with observations. And one of the ways that we do it is we use some insight into how we expect, in particular, gas to interact with a stellar spiral pattern, right? I'm showing here a graphic. This is for a density wave, right? It's the red arm here. Well, because as gas starts to interact with the spiral, move into the potential, it speeds up, and that velocity leads to a shock. And that shock tends to happen upstream, of the spiral potential minimum. Now, since the gas is where the new stars form, this results in an age gradient as you move across your spiral arm. So people can look for those sorts of age gradients because it's a very different prediction than when you have a material arm. Then everything sort of falls into the potential minimum and forms stars there. So we can look for these age gradients and for these azimuthal offsets. The other thing that we can do is we can introduce kinematic information and measure things like pattern speeds. The pattern speed is the angular rate at which the pattern is rotating. For a density wave or rigidly rotating mode, the pattern speed is constant like this, and omega here is all, the angular frequency of all the other disk material, stars or gas or whatever. And a material spiral pattern, on the other hand, kind of by definition, is going to drag around with the disk material. Okay, so if we can measure those two pattern speeds, we can infer something about the nature of the spirals. Now, this question of spiral nature, it's like, come on, why does it really matter? Well, JWST is making it relevant even more outside of the local universe, right? We see spirals at much earlier cosmic time than we had before, right? James Webb shows us the stellar distribution. HST was only picking out the tip of the iceberg. Now we can see global spiral patterns. Why does this matter? Well, we've known for some decades that spirals can influence the properties of their host galaxies. So if you put a spiral in a disk at earlier time, you give that spiral much longer to be active and in changing its global galaxy properties than if it weren't there at that time. So what do I mean when I talk about the decades-long insight that we have into the influence of spirals? Well, that starts here, right? This is angular momentum transport, written about by Donald and Bell, of course. This angular momentum transport is the result of the fact that you have a density wave perturbation in your potential that exerts torques. Those torques lead to angular momentum changes that wants to reshuffle the mass distribution, moving things inward at small radii and moving things outward at large radii. Now that happens over long periods of time, but there's also subtle radial changes that we can observe through the processes that are called radial migration. You probably are familiar with this. There's churning, which is a local change in the angular momentum of your star on its orbit or your pocket of gas. And then there's blurring, which is just an increase in the ellipticity of your orbit, giving a little bit more radial energy than we had before. Now, just like the angular momentum transport, the efficiency with which these processes act totally depends on the nature of the spiral, whether it's a density wave or it's a material pattern, whether it's short-lived or long-lived, and even properties of the spiral, whether it's tightly wrapped and exerts a strong radial force, or whether it's more loosely wrapped and includes also azimuthal forcing. So I think we don't know enough about the nature of spirals, and that's sort of my topic of interest today. Now, one of the ways that I like to go about thinking about spirals, looking at spirals, wondering how they work, is using gas as a tracer. The reason why are twofold, well, multiple fold, but let's just go with the big two. Number one, we know that gas responds strongly to a gravitational potential perturbation, to gravitational forcing. And that means that it's easy to observe the effect on the gas. Also, the gas that I like is cold, dense gas, so it's dynamically very, very cool. This makes the burden of translating between observed motions and motions in response to the galactic potential much, much easier. For practical reasons, I think this interest in using gas as a spiral tracer coincides very nicely with this era that we find ourselves in, which is the dominance of AMA and James Webb, right? So let me show you our view of the gas distributions of nearby galaxies. These are thumbnails from FANG's AMA, which is a 1 arcsecond survey of CO2 to 1 in basically every galaxy within 20 megaparsecs that sits on the star formation main sequence, okay? And what you can see here is there is a wide diversity of structures. We see narrow spiral arms, we see clumps, we see filaments, we see rings, we see it all. FANG's AMA at 1 arcsecond tells us not just about how much mass is in your galaxy, but where it's located. And it also tells us about the dynamical state and how close it is to forming stars. Now, FANG's AMA is a really big change in our view of the molecular gas in galaxies. This was state of the art just a few years ago. This is NGC 628 in 2 to 1, observed with IRAM. Okay, and we were all excited about this. Is fantastic. We can see that the molecular gas, the star-forming material, is organized into these grand design spirals, right? Beautiful. And this makes sense. We know that star formation happens in these grand design spirals, and here we were looking at the reservoir, out of the primordial gas. And this is our view of NGC 628 today. I should say a couple more slides throughout the talk are going to focus on this galaxy. It's become a favorite prototype. It's a nearly face-on grand design spiral. The AMA view shows us that those smooth spirals and the clumps within them break up into even smaller, clumpier objects, the molecular clouds, right? And there's a wealth of emission outside of the spiral arms. Molecular gas isn't just sitting in the arms, it's everywhere. Now, at this point, I would give a whole different talk just about FANGs. I don't have the time to tell you about that today, but I would just want to convince you to go look at the website, look at our publications. We've got a lot of great work happening to use FANGs AMA together with information coming from a number of other large programs with MUSE, with James Webb, with HST. And the goal is to really reconstruct the star formation cycle. How does a cloud of gas form an H2 region and then the stellar cluster from there? And the reason why we're looking at high spectral resolution is because we want to reach the scales of the clouds, of the H2 regions, and of the clusters. So that's really the goal of FANGs. Again, I don't have the time to tell you so much about it. But a lot of what we're interested in the dynamics working group is gas and star formation in the context of this global galactic environment, which is rife with bars and spirals and all sorts of wonderful structures. And what we tend to do, at the very least, is in dynamics, we make accessible to the team descriptions of that galactic environment, from the morphological features, the stellar density, the gravitational potential, and kinematics, right? And then people can then look at how star formation varies as a function of galactic environment. That's wonderful, right? But of course, we're also interested in other things. In 2 slides, I'll explain to you how we are using the galactic potential and our knowledge of it to explain how gas is structured and organized and moving. And we also can use FANGs, AMA, and other data sets to probe the nature of those spirals, right? We want to know which spiral is a density wave, which one is a material pattern. We can make those distinctions by looking at the non-circular gas motions, which are arising from our density waves, right? We can look at pattern speeds. We're measuring those. We can also, we're now beginning to look at those angular offsets to distinguish between density wave and material. So right now I want to briefly mention the work of PhD student Sophia Stuber, who was comparing the morphology of the galaxy, the global morphology of the galaxy as you observe it in CO, and compare it to the global morphology as you observe it at 3.6 microns, IRAC1, where you're tracing the light from the oldest stars, so you're tracing the stellar mass. And she coordinated the classifications of everyone. And we were following a classification scheme which was very similar to like a Buta or a Devakula or like a Hubble type of classification. And what she found, right, was that oftentimes, if you were to look at the CO in the top, you would guess pretty closely what the underlying morphology was. And that's great, okay? So the classifications would be consistent. But you won't be surprised when I tell you that's not always true. There are plenty of cases where there's no way you would have guessed that there was a grand design spiral underneath because you see something flocculent. There's no way you would guess that there was a large-scale bar in it because you just don't see it. Course. And there are plenty of cases where the CO emitting disk is quite a bit more compact than the stellar disk. And Sophia looked in particular at the bars because they were really interesting, right? And what she found is that the structure of the gas distribution, for example, the blue curves here, that varied as a function of the bar property following basic expectation. So stronger bars lead to different dust lane features. But it also depended on the gas fraction, how much gas was sitting around, how big was the gas reservoir. And that sort of melds nicely with theory, which expects that not just the bar, but also the hydrodynamics of the gas is important for how it's structured and organized, right? It matters what the Jeans length is in the gas, what structure you're going to get out of it. And the main point here is when you compare CO morphology with stellar morphology, you expect differences because the molecular gas isn't composed in a series of discrete ballistic clouds that just are tracers rotating around in your galactic potential. No, they do their own thing. It's nearly self-gravitating. It's a turbulent sticky fluid. It's collisional. It does its own thing in the potential. Now, one of the ways I think you can also see that is by looking at density contrasts. So let me step you through a result from 2 years ago where we looked at the CO on the left and we compared it to the stellar morphology. And you can kind of see by eye already that there's sort of like a smooth, low contrast stellar spiral, but then by the time you look at the gas, it's much sharper. The contrast is much higher. And we wanted to be more than just qualitative about this. We wanted to quantify exactly the difference in contrast as you move from the stars to the gas. So what we did was we divided each galaxy into a series of elliptical annuli. Then we drew a distribution, a PDF of CO and stellar brightness. And then from each PDF, we measured a contrast, say, between the median of the PDF and the 84th or 90th percentile or what have you. Okay, so the black here is the stellar PDF at a given ring, and then the blue, as you can believe, has the much larger dynamic range in intensities and densities, right, than the stars. So what we find when we plot them against each other is this. Now let me step you through it. There's probably at least 3 or 4 different conclusions one can draw just from looking at this plot. So let me take you through it. Number 1, look at those stellar contrasts. This is log of the stellar contrast. They're small. Okay, and there was a time when people said any stellar contrast you're observing is probably really just an artifact of you not properly applying the mass-light ratio to remove age and metallicity gradients, and the stellar disk is probably actually smooth. No, the gas knows. Even those small contrasts, the gas knows about them. There's a correlation here, right? The larger the stellar contrast, the larger the gas contrast. And interestingly, this correlation isn't 1-to-1, it's 2-to-1. And this is roughly consistent with the idea of a hydrodynamic shock developing in the gas as it moves in the spiral potential. So just briefly, we know that a hydrodynamic shock, the contrast in the gas is proportional to the Mach number squared, and the velocity here that's relevant is the motion with respect to the spiral. And that goes like the density contrast. So in the end, you expect a superlinear relation between the gas contrast and the stellar contrast, and that's roughly what we measure. Now it's interesting, I think, that if you look at the type of spiral that's in these disks, grand design, multi-arm, flocculent, you see the same thing. They're all obeying this hydrodynamic shock relation, right? I think that's interesting. You can ask me about it later. And the other thing that you can see here is, come on, Sharon, there's loads of scatter here. Yes, and that's the good stuff. That is self-gravity. So you have gas responding not just to the underlying stellar potential, but doing its own little thing, adding on top. Okay? So I think one of the ways that we can see the role or the influence of self-gravity on gas structure is clearest when we look, of course, at the clouds. This is where the gas starts to get clumpy under its own self-gravity. I think this is even clearer when we look at our new James Webb images. So this is 770 wide of exactly the same galaxy. I'm going to blow it up here so you can see a little bit better. Now, this is pH emission, which we're using now as a tracer of the neutral gas in our targets. You know, these 770, 1130, they don't just trace obscured star formation in the hot dust. They are tracers of the gas in our systems. And thanks to the properties of James Webb and MIRI, this is some of our highest spatial resolution maps of the gas in existence to date, with some of the highest sensitivity. So we're able to probe now into those interarm regions and transform what were just the tips of the iceberg again into all these beautiful, long filamentary structures in the interarm. Now we've been looking in a series of papers in the last year about the nature of that structure and its relation to star formation. Okay, I'm going to give you my own perspective here. I think we can see 3 main regimes, 3 different spatial scales of structure. The first one is, of course, that large-scale grand design 2-armed spiral pattern. The second one is all that intermediate scale interarm filament structure. And then if you were to look even closer, you'd see that there was another smaller scale set of features, which are the feedback-driven shells and bubbles. So let's look there first. I'm just going to summarize for you the work of Liz Watkins. She looked in detail at our 770 wide image of 628, and she detected everything that she thought was reminiscent of a shell or bubble. that would be driven by feedback. And sometimes it was a full circle, sometimes it was a little bit of a little portion of a shell, okay? And what she did was she looked at those features and she looked at them side by side with a B-band image to be sure that there was a candidate powering stellar population somewhere near the bubble or the center of the bubble. And what you can see, right away is that all of those candidate supernova feedback-driven shells, they're all lined up along the spiral arm, right? That's where the stars form. We know that. They form where the gas is dense. I just want to pick out another interesting thing. Here's a couple that you can pick out by eye. Now, when I show this, people feel relieved because they think, whew, it's not quite as challenging to identify these bubbles as you might have guessed. They are very uniform. Look at, I'm going to go back and forth. Look, these are all circular and they're all roughly the same size. So when you know what to look for, it actually gets really easy to pick those things out, right? And you won't be too surprised when I tell you that those bubbles are sized to the disk scale height. Now, there are some exceptions like this phantom void, and I think that's a case where we have supernova feedback going off not at high density like in the spiral arms, but in an initially lower density medium. And the power injected by the supernova makes the shell expand much further. Okay, but this is all consistent with what we see in simulations, right? There have been now a series of papers looking at how feedback-driven shells evolve, okay, and what they find is that there's sort of two regimes. There's one regime in which your supernova shell doesn't have nearly enough energy to go beyond a few parsecs. It stalls below the scale height. And then you have the shells, or the bubbles, that expand and lead to outflows. But the thing that we get in all these cases, when you're powerful enough to drive an outflow, you stop expanding in the plane because you've used all that energy now. Instead of pushing out in the plane in the high density portions, you've used it to now drive a low density, high temperature outflow. So in both of those cases, feedback-driven shells are on the scale height of the disk, not bigger. And you can also see from the morphologies of those shells, right, they're very, very circular. And this tells us that anything that isn't circular can't be just a bubble that was sheared out. Okay, it just can't be. The expansion velocities are way too high, given the amount of shear that we see. If you were to make one of those filaments in the interarm region, which have roughly the same small dimension as the bubble, if you were to let those things shear out, you'd have to have a much lower expansion velocity than we know we observe. Okay, so we have structure on small scales driven by feedback, but what about those intermediate and larger scales, right? What about all that other structure that we see there? How does it form? Where does it come from? Well, to answer that question, we need to go back to our theory of spiral formation or disk fragmentation. You all know this. I know you do. This is nothing more than Toomre instability and the evolution of Lin-Shu spiral waves, right? Let me just remind you here that what Lin-Shu and Kalnas did was they looked at perturbations, wave-like perturbations. They inserted them into their equations of motion, and they derived a dispersion relation that looks like this. I'll go in a little bit more detail in the slides, so don't worry. But I just wanted to remind everyone that the Toomre ring instability is the axisymmetric limit of the tight winding limit that Lin-Shu adopted here. Okay, so Toomre and Lin-Shu, they're kind of telling us about the same thing. We're looking at the evolution of a disk to the same sorts of structures, right? And so let's talk about Toomre instability a little bit. We have our cylindrical disk of gas, right? It's going to want to fragment. Okay, but there's two things that prevent it from doing that. Number one, on the small scales, we have gas pressure. Okay, and then if you set the gas disk rotating, that is also going to oppose self-gravity. But you get left a little sweet spot in the middle, and that's where Toomre instability occurs, right here at the maximum growth rate. Now, if you take the properties of stellar disks or gas disks or whatever you want, then the Toomre length sits at a few kpc. But this is good because this is the scale at which we observe a lot of structure. The thing that I think in some communities often gets forgotten, though, is that it's wonderful that the Toomre length is a few kpc. We're done, right? Spirals form through Toomre instability, but they're forgetting a couple of things. That only works as long as you also pass the Toomre threshold. This is rotation and pressure balancing against the gas self-gravity, right? You only get structure at the Toomre length if Q is less than 1. Well, let's look at the gas disks of nearby galaxies, and let's look at stellar disks. Oftentimes, Q for gas is 2 at the minimum, at the bare minimum. Mostly it's 10 and higher. What about for the stellar disks? Well, also, they're above 1. They sit above 1. And you might say, okay, that's no problem, Sharon, because we understand that spirals are the structures that form in the combined gas and stellar disk. And you say, since the 90s, we're going to make our favorite combination of Q, and 1/2 plus 1/2 is 1, and the combined gas plus stellar disk has a Toomre Q of 1, problem solved, right? The problem is that even if you have, again, the right spatial scale, even the combined Q is oftentimes above 1. Spirals aren't forming through Toomre instability. And even if you're lucky enough to get Q of roughly 1, there's still the issue that those predictions apply to tightly wound structures, rings even, right? Where all the structure that we're observing is very, very far from sitting near that regime. These are open spirals with much larger pitch angles. And then the other issue that we see now, thanks to James Webb, is that there was plenty of structure in the gas disks on these intermediate scales that had no counterpart in the stars. You can't invoke the combined disk instability to describe the formation of all that structure. So what do we do, right? This is all those interarm filaments. How are they forming? Well, we can learn a few things by looking in a little bit more detail, right? We know that these things have, well, they're long, right? They're highly regular. They have fixed spacings, and the spacings between them are between the scale height and the Toomre length, okay? And they're just everywhere. I mean, it's not just 628 where we have this problem to solve. We see them when we look at barred galaxies. There's tons of gas in that the bar-dominated part of the potential where we didn't see it before. And we also see all these filaments in galaxies where there's just not sufficient feedback to even blow a bubble. I mean, the star formation, the global star formation of IC 5332 here is really puny. We didn't even detect it in CO. That shows you how little star formation there is. So what is going on here? How do we explain the formation of these structures? Well, I think to do that, we need to revisit disk instability, right? Remember, we started off with the tightly wound dispersion relation here, which is related to axisymmetric Toomre ring instability. But what happens when we want to talk about more open spirals with larger pitch angles? What then? Because this is what we need to do. We need to solve the formation of these sorts of structures. What do we do? Well, unfortunately, as we've known for a while, there are no solutions to the Lin-Shu dispersion relation in that limit. Okay? We need to do something else. And that something else is what I'll tell you about for the last little bit here. And what I want to just briefly say is that something else, a little bit of a spoiler here, is that you have to have your spiral shearing, or at least sit it in a shearing disk. Okay. Let me take a step back here and now motivate a new mindset when we think about spiral structure formation. Now, for the past 30 more years, right, when we think about spirals and the challenge of creating them, we usually think of this in terms of an isolated galaxy simulation. It starts off as a smooth disk, and somehow we have to get a spiral to form, okay, and evolve. I think this is probably too challenging of a problem to solve, considering that most galaxies aren't isolated disks, okay? They're constantly being perturbed by dark matter halo substructure, by orbiting globular clusters, the molecular clouds, right? In fact, it seems like there's probably too many perturbations now to get just one or two that dominate the spiral pattern. But that's now the challenge. Not just how any single perturbation originates, but why out of a sea of perturbations, only one or two get selected for growth. So that's the problem we're trying to solve. And the way that we do this is using standard techniques, okay? I'm going to adopt the hydrodynamic equations. This is the equation of continuity, the Euler equations, Poisson's equations, okay? And I stick in perturbations like here at the top. These are standard, right? We have a radial wavelength k that tells us about the radial separation between spirals. We have some angular wave number m over r, which tells us about how many numbers of spiral arms we have, okay? Insert those into my equations of motion, linearize them, and then derive as close as possible a dispersion relation. Now, mind you, this is pretty basic. There are no magnetic fields, there's no viscosity. I'm talking about very, very cold, dense gas with high Reynolds numbers. There is no star formation feedback. But that doesn't bother me. This is what people have been doing for a while now. Now, what do we get? I'll spare you the detail. Oh, let me talk about one more point here. The third thing that we need to do to move beyond Lin-Shu was we need to think about a broader set of perturbations. Now, normally when people calculate dispersion relations, they start off already looking at modes. But we're going to have to allow explicitly that there's radial variation in the pattern speed. We're going to also allow explicitly that we're looking at amplifying or potentially growing modes, right? And the reason why we're doing that is because we're going to go outside of this Q equals 1 regime. Oftentimes people start at like Q equals 1 and think the thing is quasi-static, and so we're going to have quasi-static spirals, and we're going to toss out any growth, right? And I think we need to keep that in. We need to think about what happens when Q goes above 1. And then the last thing is that we're going to remember, we're going to look outside the tight winding limit. We have to look at open spirals because that's the structure that we observe in disks. Now, let me just remind you here, the tight winding limit, what we do there, what that means is that the radial wave number is much, much larger than m over r. Okay, so these things are really, really tightly wrapped. All right, and we usually get into the tight winding limit by adopting what's called the WKB approximation, which assumes that, take your spiral sinusoidal perturbation, the WKB approximation assumes that the phase variation is much, much more rapid than the overall variation of the amplitude of that perturbation, okay? And so that allows us to drop a lot of pesky, annoying terms and write down the Lin-Shu-Kalnass dispersion relation, right? And that led us to, this is epicyclic motion or rotation and pressure acting against self-gravity. You can see it right there. Normally what we do is we solve it, we find real K, and that allowed us to see how the Toomre parameter came in here, right? We're only going to get real solutions for K if you're above Toomre Q equals 1. That means you're not going to get growth if you're above Toomre Q equals 1. Okay, what about in this open regime? We have to do things that are different. But we're going to play a little trick. Now, in this open regime, I'm going to require that Kr is comparable to M. But I'm still going to invoke the WKB approximation. And the reason I get to do that is because I'm only caring about large M. So M can be large as well. That means I get to have all of the benefit of adopting the WKB approximation. I get to drop all of these global terms, right? 1 over R, the change in the density. Okay, and I argue that we can do that because we're interested in those sorts of high M structures, right? And you can do this, you can invoke the WKB approximation and look at a high M structure as long as you know that at any given radius, you're sampling many Jeans lengths, right? Now, the structures that are going to form are not sitting near the Jeans length. So you can invoke a high M and not be contradicting the WKB approximation. Okay, so again, I'm going to spare you the details of the derivation and just show you what we get. That is in the rectangular box here. In the gray box, I just have some definitions of the parameters that are appearing in this equation. A couple of things I want to point out. First, it's a cubic dispersion relation, not quadratic, like the Lin-Shu dispersion relation, okay? And there is a linear term, which is imaginary. If you're going to solve that dispersion relation, that tells us that you're immediately going to get growth or decay. No Toomre Q involved. You're immediately going to get growth or decay when you've got a cubic dispersion relation with an imaginary part. Okay, and as it turns out, right, that imaginary term, which is the interesting term here, that was 0 in the tight winding limit as m went to 0. Okay, it wasn't in Lin-Shu. It's also 0 as the Oort constant A here, which is a measure of rotational shear, when that goes to 0. Now, that top term, right, that's the conventional stability regime. If you were to let m equal 0, you'd get that conventional stability back, just like Lin and Shu. But as m departs from 0, then you get mostly this imaginary term, which dominates everywhere Q is above 1. So this is going to dominate the evolution of your structure anywhere above Q equals 1. Now you can see already from the language on the slide and the way I've been talking about it, yes, this is very, very similar to swing amplification, okay? But recall, swing amplification, our description of it so far is kind of limited, okay? You take your disk, you look at a tiny little patch, you look at the evolution of your densities in shearing coordinates centered on that little patch, and that's great and all, right? But what we have now is we have an ability to describe swing amplification in a global context, and in particular from within the context of a Lin-Shu framework. So we're seeing swing amplification now with a Lin-Shu type, or Lin-Shu Kalnas type of procedure. And the reason I think for doing this is because you just learn so much. Okay, now we can see that the amplification is really sensitive to the spiral forcing, not this coordination between shear and epicyclic motion. No, it has everything to do with the forcing exerted by the spiral. And because that is the case, and because we have this new framework now for looking at how non-axisymmetric structures amplify, we can also now make concrete predictions for the angles and the pitch angles of the structures that are going to go on to dominate the morphological appearance of your disk. Let me show you why. So let's just think about that. So I'll back up and say that you have a cubic dispersion relation. You're going to get three sorts of solutions to it. I'm going to focus on one. That's when, the relative angular speed is 0. And that means that all of omega is imaginary. Right? That's what I'm showing here. Now, how do we get omega minus m omega equal to 0? In two different ways. We can either have a material pattern, where by definition those things are 0, or we can be looking at a mode simply at its corotation. That's also where you get 0 there. And in these two regimes, all of your solution to the cubic dispersion relation is entirely imaginary, and all you need to do to get growth now is a few things. But let me just say, just for the heck of it, this was derived with the hydrodynamic equations, but it's also a very, very good approximation for stellar disks, as long as you're looking above the Jeans length. Okay, this is to second order you would derive something just like this to second order if instead of having pressure, you took into account the weakening of the self-gravity because of the velocity dispersion in the stars. You can ask me more questions about it later if you'd like. I'm just going to say that everything that we talk about from here on out applies equally to gas structures as it does to stars. Okay, so how do we get growth? I'm interested in growth. I want to see these things amplify, not decay. In order to get growth, we need to have omega I, this omega I bigger than 0. And you can see from the expression that you can do that as long as you're above the Jeans length, right? So that the term in parentheses is positive. And you can do that, in that case, only when your wave is trailing, so when k equals 0. There is no Q criterion here. There's nothing similar that comes out, okay? All that matters for whether you get a local instability or not is what the properties of the spiral was about its radial wavelength and wave number. So the constraint isn't on Q or relying on Q. It only depends on the properties of the spiral. And let me just back this up here because I think this is really the audience to talk about this. Recall that when we introduce a non-zero m, what we're doing is we're introducing a non-negligible azimuthal force. Before it was all the radial force. Okay, now we open it up, and now the azimuthal force becomes equally important. And what we do when we play around with the azimuthal force is we introduce donkey behavior. Okay, let me step you through the donkey effect. You should all know it very well. It should be near and dear to your hearts. I'll just step you through a little bit of the work that we looked at when we went into the spiral arm frame in this work, right? Here's my spiral arm. It's this black curve here, and the dotted part is when I move into this sort of interarm regime, okay? And I'm going to set rotation in this direction. And then radius is into and out of the board, right? Remember what Lindenbell and Kalnas wrote about in 72 was the fact that, okay, we understand, take a star or a pocket of gas, and you set it interacting with your potential. It's going to be forced towards the potential minimum. Okay, but what happens because of the way that disks behave is that the acceleration is actually in the reverse direction. And that has everything to do with the way that the angular momentum is distributed in galaxy disks. And so we have donkey behavior, as Lyndon Bell described it. In azimuth, stars behave like donkeys. They slow down when they're pulled forwards, and they speed up when they're pulled back. And he also showed us in that paper how this was really key for wave amplification, okay? Because when you slow down your orbiting star or your pocket of gas, it wants to take energy from the wave, and that removal of energy actually helps the wave amplify. Now, you probably are thinking, okay, so it's so important to have this donkey behavior incorporated. So you're right, there's going to be a critical pitch angle at which the donkey effect can come on in full force. And that's what we see when we plot the growth rate here on the vertical axis as a function of the pitch angle of your spiral, and each line is a different multiplicity, okay, normalized to the gene's length. Or it's the azimuthal wave number normalized to the gene's length. And what you can see here is that there is a critical pitch angle at which growth maximizes, right? Now you've sort of taken advantage of not just the radial forcing, but the azimuthal one, and you've worked and worked until your pitch angle was right to sort of capitalize on both at the same time, and that leads to the amplification. Now I've translated that into the plot on the right, which just shows you the location of that peak, right, as a function of that spiral multiplicity. So this is where you're going to get fastest growth. Now, when you think about, material patterns, we need to think of these things as amplifying, again, not because of this coordination between epicyclic motion and shear, okay, well, that's happening a little bit when you look in the radial direction. No, we need to think of these things as amplifying because they've swung through this critical angle, which is where the forcing was able to support a growing wave. And then at some point later, of course, right, so here we are swinging through my critical orientation, my amplitude increases, but at some point later, I have the wrong pitch angle anymore to tap into the donkey behavior. And so the growth shuts off. Well, now we can look at the same sort of plots and interpret what's going on when we think about wave modes, not shearing patterns. So K, or the pitch angle, is not going to evolve in time. These things are fixed, right? But we're also going to have growth limited to this critical orientation for exactly the same reason. Okay, now imagine you have a sea of perturbations. The one at the critical orientation is the one that's going to grow to dominate. That's what we're looking at here. But it's probably easier for us to look at this in slightly different terms. Now I'm plotting the growth rate as a function of spiral multiplicity for different values of the radial wave norm. I'm sorry it's not appearing, but what you can see here is that just like before, you get this maximum growth at a particular value of m for a given k. And I've translated that into this plot here. So this curve here is showing the location of the peak k for a given m. Now, this, just to use the language that we've used before, right, this is where we have weak donkey behavior at small m. Okay, we pass to a regime now where m is large enough to tap into the azimuthal force that turns on donkey behavior and the wave amplification. And then for any pattern that's away from that, we don't get amplification. And in fact, if you start having so many spiral arms that the distance between them now sits near the gene's length, then pressure is going to inhibit any sort of structure formation. So you have donkey effect on one end and pressure on the other. And you're going to find that spirals, the multiplicity of the spiral is such that the spacing between fragments is always going to be a few genes lengths. Okay, that's what's translated here into this. This is like anywhere between 2 and 5 over a large range in K. Now, interestingly, I don't have that much time to talk about it, but for these amplifying modes of corotation, the growth is also transient. This might be counterintuitive, but it stems from the importance of the donkey effect. It's totally possible for your spiral to amplify happily, but it gets too big, all right? And the forcing changes, and it no longer elicits donkey behavior anymore. So when it's grown too big, donkey behavior stops, the growth saturates, right? And you have the end of your spiral. Now, given these predictions, right, we can think now about what sorts of disks give rise or favor certain types of structures, right? If you take a stellar disk, it's dynamically hot, gene's length is big, those sorts of systems favor only a few spiral arms. The spacing between arms has to be big. You're going to get 2 to 5 spiral arms. If you look at a dynamically cooled disk, the Jeans length gets much smaller, and now you can sit many, many more spiral segments in closer and closer to each other. And in fact, you're going to typically get anywhere between 40 and 50 of these little spiral segments. And I think that's very, very close to what we observe. Let me just take you back now to NGC 628. We measured this, okay? Here's 628. We wanted to look at the spacings between those filaments and then compare them with these predictions. So we used a tool, Fill Finder, okay? We made a filament mask like this. Then, we looked in a series of elliptical annuli at the spacings from one filament and its neighbor. And we measured those and put those on this plot here. So the black points are the spacing measurements, and then there are some reference scales. So there's the scale height of the disk in red, there's the Jeans length in gray, and then the most unstable 2D mode length, which is a factor of 2 smaller than the Toomre length, is there as well. And just what you expect, right? These things are sitting above the Jeans length. And for reference, if we plot those bubbles that Liz identified, they're all sitting down there at the scale height, like the simulations and theory tells us they should be. Okay, so my takeaway is that we can get loads of structures in disks, even above Q equals 1. The other thing is that modes amplify very, very similarly to material patterns. I know this is also something that we're not used to thinking about, right? But the physics, the process is the same, and it's the donkey effect. It has to do with the forcing of the spiral, okay? But because modes and material patterns amplify very similarly, it kind of gets hard to distinguish between them again. We can't use the pitch angle of the spiral anymore to tell us if we had a mode or a material pattern, like some people have tried to do. And then the other takeaway that I just like to leave you with is that, yes, each of these individual patterns is short-lived, okay? But the pattern that you get, that critical angle, depended on the local disk conditions. So even though any individual pattern is short-lived, it's going to be replaced by an almost identical pattern. And you're going to be able in this way to stitch together a long-lived spiral pattern. Any individual spiral is short-lived, but you can have a spiral that's present and active and doing things, wonderful things, for much longer. Now, I've been told I have to really stop at 50, but I just wanted to leave you with a few other thoughts, and that is to remind you, all right, this is not the first time we're saying this, that spirals are probably each individually transient, but together stitch a global spiral pattern. Right. A few other things I wanted to leave you with. Don't forget that the gas is quirky because it responds not just to the underlying stellar spiral pattern, but it wants to grow its own structures. And it does that because it is self-gravitating. And then we have a wealth of structures that we can now predict on the gene scale. It's very consistent with the structure we observe in gas disks. But because now we have all of these open structures, open spirals, this is going to play a very, very similar role as spirals in dynamical heating, molecular clouds in dynamical heating, because what are the molecular clouds but these filaments? Okay, we just looked at the tip of the iceberg. So you're going to get dynamical heating from the fact that you have all of these transient spirals. And that's the direction I think we need to be looking, and this is what I'm working on right now, is to actually estimate what role transient spirals play in the observed non-thermal motions in gas. I think I'll leave at that and see if there are any questions.